So you've found the perfect home. But high mortgage rates have you second-guessing. The Churchill Mortgage team says waiting to buy can be a costly mistake. Try their free 15-minute analysis to see the difference between buying now versus waiting for lower rates. Visit churchillmortgage.com to learn a smarter way to build wealth through home ownership. This is a paid advertisement. NMLS ID 1591. NMLS ConsumerAccess.org. Equal Housing Lender. 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027.
With Kroger brand products from Bakers, you can make all your favorite things this holiday season. Because Kroger brand's proven quality products come at exceptionally low prices. And with a money-back quality guarantee, every dish is sure to be a favorite.
These are a few of my favorite things.
Whether you shop delivery, pickup, or in-store, Kroger brand has all your favorite things. Bakers, fresh for everyone.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello, and thank you again for joining us on Space Nuts, where we talk astronomy, space science, and anything else interesting that's happening in heaven and here on Earth. My name is Andrew Dunkley, your host, and this week we're going to be looking at a little bit of a moon mystery. The moon's magnetic field has made the news, so we'll have a look at that. A gigantic exoplanet has been found under unusual circumstances, is the way I read this story. And we got a listener tip the other day, which we're going to follow up. There's a bit of a search on for a Falcon Rocket body, and they think it might have crashed into the moon, and they're asking amateur astronomers and space photographers to maybe provide some information that might help them find it. So we'll tell you about that a little later, and thanks for sending that in. And questions, surprisingly, about the James Webb Telescope and the James Webb Telescope and the Oort Cloud, and a couple other things we're going to chuck in for free on this week's episode of Space Nuts. Joining me, as always, of course, is his good self, Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How are you doing this morning?
I am quite well, thank you, sir. Survived 35 years of marriage, so yes, all is well.
Congratulations. That's an achievement.
Yes, that was. We had our anniversary this week, 35 years. We both woke up and went, 35 years, really? It just doesn't feel that long.
No, that's nice. But it's good. Well, you're still in love and still you young people.
I never said that. Yeah, of course we are. No, it's lovely. We went out for dinner and
lovely,
and just sat there and sort of pondered our 35 years and wondered where it all went. And yeah, we'll push on for 35 more. Not sure we'll get that, but
I think we'll
give it a crack.
Yep. You've got a few youngsters around to demonstrate where it all went.
That's very true. Yeah, 4 grandchildren now as of November.
Yeah.
Now, Fred, let us get down to the business of talking astronomy and space science, and we are looking at the mystery of the moon's magnetic field, and I'm gathering from just glossing my eyes over this story that this sort of is something they've analysed through historic samples, historic data. Is that right?
Yeah, indeed. It's from the Apollo mission sample returns back in the 1960s and 70s. Let me see if I can remember the number. I think it was 387 or thereabouts kilograms of material came back from the moon. It's
which is why it's moving away from us, because it's so much lighter now.
Lighter than it was. That's right. Yeah, it's a significant amount that was brought back. I might have that number wrong, but it's usually in my head, but it's a bit vague at the moment. It's there that sort of order anyway. So that material was brought back and has been, in many ways, it's one of the greatest scientific treasure troves that we've ever had, because it's taught us so much about not just the moon and its origin, but the origin of the Earth and indeed the origin of the solar system. It's been absolutely fantastic.
What number did you say?
I said 387.
382.
All right, that's not bad. Maybe I'm not
Pretty good,
losing it
pretty
as much as I
A
thought.
7
it
can
was.
look like a 2 sometimes.
Yes, that's right. Yeah, that's good. Oh, thanks for that. That's cheered me up no end. So now the bottom line is that the moon doesn't have a magnetic field today. That's one of the things that's been known since the early days of the space age. In contrast with the Earth, which has got a fairly substantial magnetic field, the moon doesn't. But some of those rock samples that have been brought back have evidence within them that tell you that they formed in the presence of a strong magnetic field, one that, in fact, probably comparable with the Earth's magnetic field. So that's really interesting because, well, first of all, there ain't a magnetic field now. So what happened to it? But secondly, you've got evidence that from the rocks that the rocks formed in the presence of a magnetic field and a strong magnetic field. How does a body the size of the moon, a quarter of the diameter of the Earth, 1/80th of the mass of the Earth, how does a body that size generate a magnetic field as strong as the Earth's magnetic field?
Yeah.
And that's the big mystery. That is, number one is, where's the magnetic field gone? Number two is, how on earth did you manage to demonstrate, to actually, for the moon to produce a magnetic field that strong? Now, this has created a 50-year-old mystery, and it now seems to have either, I think we could say it's been resolved, but probably what a better way of putting it is that there is a new explanation that has been proposed for this magnetic mystery, and it comes from scientists at Brown University in the USA. So essentially, what these scientists have done, and actually there's one of the lead authors is also from Stanford University, just to get the attributions correct. What they've done is looked at models of the moon's internal structure during its early history. And it seems that you could get a situation where rocks, if you think of the moon as having a core and a mantle, which is what the Earth has got. The Earth's got the same sort of structure. And the mantle is that region where the rock is fairly soft and moves around by convection. And in the Earth's case, that causes the plate tectonics, because it's the convection within the mantle that provides the energy to drive the shifting continental plates and oceanic crust. So plate tectonics is driven by convection in the mantle. So if you think about that, the way these flows of magma go up and down in the mantle, but think about it in the moon. They've come to the conclusion that there are bodies of rock, sort of semi-liquid rock, which can move through the interior of the moon relatively quickly, and by doing that, generate magnetic fields. And partly that's due to some of the materials within them. Things like titanium, which are actually within these rocks, a high density of titanium, so that's a metallic thing. And that, intuitively, you can, certainly for somebody who's a non-expert on this sort of thing like me, I can get the impression that might churn up some magnetic fields. But there's details in this study that really lead them to have, I think, a fairly high degree of confidence that this is going to produce the kind of magnetic fields that have been observed. So I'm just trying to find a quote from one of the authors, which this actually is Alexander Evans, who's at Brown University, as I mentioned. And Alexander says, everything we've thought about how magnetic fields are generated by planetary cores tells us that a body of the moon's size should not be able to generate a field that's as strong as Earth's. But instead of thinking about how to power a strong magnetic field continuously over billions of years, maybe there's a way to get a high intensity field intermittently. Our model shows how that can happen, and it's consistent with what we know about the moon's interior. And it is all about these churning, blobs of material going up and down in the moon's mantle, the region around the core. They suggest that these are actually as small as 60 kilometers in diameter. And these are the titanium formations I mentioned before. And they sink over the course of about 1 billion years. So, it's not a fast forward thing, it's a relatively slow process. But what they suggest is that when these blobs of material hit the bottom, and by the bottom they mean the moon's core itself, then they basically stir up what is called the moon's core dynamo, and that's presumably because the moon has a metallic core. They stir that up and generate these high magnetic fields for a short period, partly because the things that are the blobs of titanium-rich material that are flowing down are much cooler than the core temperature of the moon. And so there's a sort of bang when this happens, generating a magnetic field at the surface that is really strong, like the Earth's. And they suggest, here's a comment from one of the other authors in this paper. You can think of it a little bit like a drop of water hitting a hot skillet. You've got something really cold that touches the core, and suddenly a lot of heat can flux out. That causes churning in the core to increase, which gives you these intermittently strong magnetic fields. And as many as 100 of these downwelling events over the moon's first 1 billion years have been postulated, and each one could produce a magnetic field that might last 100 years or so. And so that's where these magnetic signatures come from in the Apollo rock samples. And one other thing that perhaps, in a sense supports this theory is that some of the other rock samples that came back with the Apollo astronauts show no evidence of having a magnetic signature. There isn't the alignment of grains that you find when there's been a strong magnetic field.
I was going to ask you how they can figure it out by looking at the rocks, but you just said it, the alignment.
Yeah, that's right. Sorry, I meant to mention that right at the start of this, Andrew.
No, that's okay. I would have asked.
Well, you did. So it's all about the alignment of the grain structure in the material.
Okay. Yeah, that's fascinating. I suppose when you think about it, rocks tell us a lot of things, like rock samples on Mars are going to tell us about water presence and perhaps former life. I think geology plays a very big role in us understanding how things were over periods of time that we didn't even exist as a species.
Yes, that's right.
And that's fascinating.
One of the other things, just a bit more closely related to what we're talking about, though, that it's rock samples from beneath the ocean bed that tell us about magnetic reversals on the Earth's magnetic field. The fact that we know that every, maybe 2 or 3 times per million years, the Earth's magnetic field swaps, so the north magnetic pole becomes the south.
I've actually seen a rock like that, and what had happened was that somebody had drawn an N at the top of it, and then they'd scribbled it out and drew an N at the bottom. So I knew
that's what had happened.
That's what had happened. There'd been a reversal.
That's what you call a magnetic pole reversal.
That's right.
And probably a slight reversal of logic there as well. But never mind. Never mind.
Plenty of that at my end.
Yeah.
Yes, indeed. Okay, so it looks perhaps like they may have solved the mystery of the moon's magnetic field.
It's a very nice piece of work, I think, and well done to the scientists at Brown and Stanford who've done that work. Fabulous.
Yes, indeed. Wonderful. You're listening to, and if you're on YouTube, watching Space Nuts. And it's good to have your company. Andrew Dunkley here with Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, I did mention YouTube, and if you do have a YouTube account or you like to get onto YouTube occasionally and see what's going on, we do have an official page. It's youtube.com/c/spacenuts. I'm sure if you just did a YouTube search for Space Nuts, you'd either get that really terrible sci-fi movie, which was called Space Nuts, or you would find us. If you put Space Nuts podcast in, you got a better chance. But all our episodes are there. And of course, the more recent ones are, in fact, showing our faces. That's pretty scary stuff. But if you can tolerate that, you can catch all the Space Nuts back catalogue on YouTube. We've got nearly 2,000 subscribers there, Fred, believe it or not, which is
Wow.
which
That's
is fantastic.
fantastic.
Only 100 million more, and they'll start paying us $1 a week, apparently. If you'd like to join us on YouTube, just have a look around for us, and we'd be happy to have you add to the 1.95 thousand people that are already there. Okay, Fred, a gigantic exoplanet has been found under unusual circumstances. Where is it? What is it? And who found it? And why is it unusual? In 20 words or less.
20 words or less. Well, I might quote Paul Delbar, who is, I hope I'm pronouncing his name correctly. He's an astronomer at University of California, Riverside. And this is probably more than 20 words, but it's very succinctly explains why this object, whose name is TOI 2180b, why it's important. He says, TOI 2180b is such an exciting planet to have found. It hits the trifecta of 1, having a several hundred day orbit, 2, being relatively close to Earth, 379 light years is considered close for an exoplanet, and 3, us being able to see it transit in front of its star. It is very rare for astronomers to discover a planet that checks all 3 of these boxes.
Wow.
That's more than 20 words, but that highlights.
That's fine.
Yeah, it's a big planet as well. 261 day orbit around its parent star. It's a planet whose diameter is roughly the same as Jupiter, but actually 3 times more massive. And in fact, it's unusual because it contains 105 times the mass of the Earth in elements heavier than helium and hydrogen. That means it's a what we in astronomy would call a metal-rich planet. Astronomers call a metal anything that's not hydrogen and helium. That's one of the loony things about what we do.
Yeah, that doesn't necessarily mean solid, though.
No, and it doesn't mean iron or platinum or anything like that. It also includes sodium, and sodium is a metal, but beg your pardon, it includes oxygen, and they're all metals to an astronomer. For reasons that I don't need to go into now. Anyway, it's really metal rich. But why is it a spectacular discovery, and why is it an unusual team that has found this? And it is because the TOI tells you that it was discovered by the TESS planet finding spacecraft. Was it Transiting Exoplanet Survey Satellite? I think that's what the acronym stands for. TOI stands for TESS Object of Interest, I think. Yeah. And so it was discovered by this planet having been observed to pass in front of its parent star and dip the light of its parent star slightly. And that's what TESS does. It's what Kepler used to do as well, and it's been a very, very successful way of finding exoplanets by what we call the transit method, sometimes called the wink method. I came across recently, which is a really
good
nice
name for
way
it.
of putting it. Yeah, it's the wink method, which contrasts with the other method of finding planets, which is the wobble method, the Doppler wobble, where you look for the reflex motion of a star caused by a planet pulling it slightly from side to side. And the reason I mentioned that is because they've brought that method to bear on this object. So the reason why it's unusual is that when TESS finds a candidate planet by the light of its parent star dimming slightly, that is not something you can announce as being a planet, because there might be other reasons why that star's light would dim.
Yep.
Could just be, could just be a fault in the instrument or something like that.
Dust.
Oh, yep, dust on the lens, the whole thing. But no, it's not dust on the lens. Never mind.
Lens cap.
Yeah, the lens cap. So when the TESS research team look at their data, single events are not exciting because that needn't necessarily be a planet. And so usually what they have to do to count as a discovery is see this planet pass in front of its parent star 3 times. So they need to see 3 of these transits before it's confirmed as a planet. And that's perfectly sensible because, that you've then got an idea of what the period of revolution of the planet is around its parent star. And you've got 2 estimates of that. And if they tie up together, then, you found the right thing. If you think of something in our solar system, like somebody looking towards our solar system, every year they'd see a very slight dimming as the Earth goes past.
Yeah.
Now,
If they looked at Earth directly, they'd see a lot of dimming.
yeah, they would. Oh dear, yes. Anyway, we won't go there. We're staying cheerful on Space Nuts this morning. One of the numbers that I've already mentioned should suggest that this thing probably hasn't been observed 3 times because it takes nearly a year. 2/3 of a year, 261 days to complete a journey around its star. So it's what happened was that there are other groups who look at TESS data, and these are essentially citizen scientists groups who have access to the TESS data and look through it basically manually, rather than leaving it to a computer to look for these dips in the light of a star. These folk look through it manually because they can pick up things that you don't see, that a computer would not detect. And a gentleman called Tom Jacobs, he's a member of one of these groups. He's a former US naval officer. He basically, looking through the data, saw the light of star TOI 2180 dim, and he got in touch with Paul Dalber, who we've mentioned before, and that essentially started this research because Paul Dalber's speciality is studying exoplanets that have long orbital periods. In other words, they take a long time to orbit their stars.
Yeah.
So that's a very nice symbiosis. So Dalber, being a professional astronomer, could alert the astronomical community to try and, first of all, get an idea of whether this is a real planet by looking at the wobble method, which is where you look at the way the star behaves because of the gravitational pull of the planet on it. And that's what has allowed the calculation of the mass of the planet, TOI 2180b, and, gives you some ideas of its orbit. Now, the second transit has not yet been observed, I think. There was basically a suggested one possible in August last year. And there is a suggestion that there will be another one coming up sometime in February. I think that what this is implying, Andrew, is that this is not a circular orbit, that this is a fairly elongated orbit, right, which has probably come from the wobble data. So because August to February isn't 261 days.
No.
Maybe it is, actually. Well, it's not. No, it's not. No, it's not. Top of my head. It's not. It's shorter. It's shorter than that. So it suggests that this has got an elliptical or elongated orbit. Mm-hmm. So the planet has been confirmed to exist because the wobble method has proved that, and it's got all these apparently really interesting attributes, as we've said, a giant planet. In fact, one headline is a giant planet hiding in plain sight. Yeah. And so I think it's a very exciting, an exciting object to be looking at because it is so unusual. And so when there is another transit, that will allow more data on the orbit to be detected. People are actually looking for it already, or certainly will be around the end of February. And all credit to this group of citizen scientists for flagging this. I'm a great
that's
fan
fantastic.
of citizen science. Yeah,
Really is fantastic. And it must be a delight to be able to actually have potential confirmation in such a short period of time, because I'm sure Paul gets frustrated when they discover an exoplanet and then they realise it'll be 500 years before we get the second transit, and he's got to leave a note for his great-great-great-great-great-great-great-grandchildren so that they'll have to check for him.
Well, it could be. That's right. You're talking about, it's when you think about the outer planets of the solar system, Neptune's 200 and something years. I can't remember the exact number.
Yeah, it's extraordinary. Yeah, that's a great story. Now let's move on to another search, and this one came from a listener who picked it up on a forum website, the cloudynights.com website, and they're looking for a Falcon rocket body. And they're looking, again, to citizen astronomers to help them out with this. I think this is a really good thing that people can get involved in.
That's correct. It needs a bit of careful observation. I think this is one for the amateur astronomers in the community. But this is an object. It's NORAD, which is the categorization of artificial objects in space. Its number is 40391, and apparently it's a Falcon rocket booster from earlier this decade, probably actually last decade, a few years ago. Right. Falcon, remember, is the SpaceX's flagship boosters. Nowadays they bring them back to Earth, but a few years ago they didn't. And it's in orbit around Earth, but it's been gravitationally interacting with the moon, and it's objects like this often enter chaotic orbits. They because they're very lightweight objects. They're at the whim of the gravity of the moon and the Earth and the Sun and the other planets. They often change. Their orbits are often not elliptical. They're elliptical for a little while, and then they change into something else, and then they go back to being elliptical. But now there is a chance that, first of all, the interactions with the moon have essentially sobered up the orbit of this object and given it a more predictable orbit. This is 40391, the Falcon rocket body. And there is now a chance that it will collide with the moon. In fact, in March, in a bit more than a month, about a month and a half, early March this year. And so that's a really interesting speculation. It's not something that we could ever observe because it's on the far side of the moon. But it would be great to know if this is going to happen. And so this alert on the Cloudy Nights forum, which is a very well-respected, astronomy forum, that alert is for amateur astronomers who've got the capability to do astrometry, which is measuring the directions of objects very accurately, to try and observe it. When it is in a position where it will be reasonably bright, in other words, when it's sort of if you like, in opposition, in other words, on the opposite direction from Earth to the Sun, so that you see it brightly illuminated by sunlight. It's easy to find if any of the amateur astronomers on the Space Nuts forum feel like going to Cloudy Nights, Google Falcon rocket body possible impact, and I'm sure you'll bring it up, because that has an ephemeris, at least a generator for an ephemeris. What's an ephemeris? That's a table that tells you where the object is going to be at a given time. It's a very old term, but it's still widely used in astronomy. And so it would tell you where to point your telescope. So during January and February, amateur astronomers are being alerted to do this. And any Space Nuts astronomy enthusiasts who've got the wherewithal to do it are encouraged to check it out.
Wouldn't it be awesome if one of our people did actually locate it and NORAD went, oh, it was a space nut that did that.
Yeah, it would. Yeah, absolutely.
Yeah. All right. Just do a general search. You should be able to find it, or go to the cloudynights.com forum website and look for it there. The URL here is 300 miles long, so I won't read that out because you have a bit of trouble remembering it. But it shouldn't be hard to find. Maybe NORAD would have something on their website after they've sent the boys over to check out you're okay to use their website. But yes, good luck with that. Let us know how you go if you have a crack. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
3, 2, 1.
Space Nuts.
Now, have you signed up to be a patron yet? You don't have to, but if you'd like to contribute to the show, you can do that. Just jump onto our website, spacenutspodcast.com or spacenuts.io, and you can click on the supporter button and find out how to contribute. And one of the options there that we introduced lately was to buy us a cup of coffee, which a lot of people seem to have shown a preference for, so fantastic. So, in fact, someone said to me the other day, they've bought us 3 cups of coffee already. Which is good because there are 3 of us that put all this together. So that is fantastic. If you'd like to become a patron and make a regular contribution, or just make a one-off contribution through the Buy Us a Cup of Coffee link, you can do that via our website, spacenutspodcast.com. Now, we have some questions, Fred, surprisingly. And this first question is from Wes in Florida, who's emailed us. Esteemed fellows, I must have been for a different podcast. 2 questions. If we talk of men going to Mars, why can't we service the James Webb Space Telescope, which will be significantly closer at L2? And why would you not make fully ready and test the James Webb Space Telescope for errors when it is in Earth orbit before sending it on its way to its permanent station? I'm sure there's a good answer for these, but I've not heard the argument. You're about to, Wes, because there is a good answer. And Fred has actually spoken to somebody who's at the coalface in regard to this.
Indeed, that's right. Certainly to one of the questions. The first question, why is it not surfaceable if we can go to Mars? Well, the answer is we can't go to Mars yet.
Can't go there, and it might be more than the lifespan of the James Webb Telescope by the time we get there.
That's right. That's exactly right. It's the work that needs to be done to get us to Mars, which would probably be applicable to get us to L2 as well, to have a service of JWST as well as a couple of other things that are out there.
It's probably a good option though, because you could stop and use the restrooms and have a hamburger.
One day. Look, I like your thinking there, because, as you know, I'm a great proponent. If we're going to colonize space, I think we've got to do it by artificial structures, and L2 would be a great place to put one. Get marvelous views of the Earth in darkness all the time. So so it's just the technology isn't there yet, but physically it's not impossible. But the second part of the question, I think, is essentially why didn't we
checks and balances before we started?
That's right. I'm trying to put it in a way that it was checks and balances, but I think by that our listener means actually assemble the thing before it gets sent off. And that's to do with, the deployment of the heat shield, the deployment of the mirror, and all that stuff was the risky stuff, the high risk stuff. So so I've had a bit of correspondence on that with a colleague by the name of Philip Nance, who I talk to from time to time, and he sent basically an inquiry on exactly this to John Mather, who's actually on the JWST team. And so what Phillips wrote to John was, it surprised me that as Hubble was repaired in situ, a decision wasn't made to temporarily park James Webb Telescope in an orbit from which it was readily accessible from the International Space Station. At that location, the un-origamiing of James Webb's mirror could have been monitored. Should problems have occurred, appropriate personnel could be delivered to ISS for spacewalk rectification if necessary. When carried out, the James Webb could then be boosted to Lagrange, perhaps leaving the mirror unfurled. This would have added maybe 0.01% to the mission cost, but excellent insurance value. That's Philip's question. And let me read you John's reply, which is, Dear Philip, your question was, of course, our first one. Is it possible to deploy JWST in low orbit, check it, and then boost it? The problem we encountered is that after deployment, it's not nearly as strong as when it's launched. We thought that the additional boost to L2 would have given too much vibration and would damage the telescope. In my next life, I'd like to come back and have a small booster that is much more gentle, so your idea would work. There you go. That's from the horse's mouth.
The other problem, of course, in low Earth orbit, you open the mirror and there's no way of wiping all the dead bugs off it.
Well, it's, space junk and all the rest of it, yeah.
Yeah, exactly. And that too, that would be a risk. For sure.
There could be dead bugs out there, Andrew. It's one of the interesting things. They found microbes on the outside of the International Space Station.
And tardigrades.
Yeah, well, there's lots of tardigrades around, yes.
All right. Thank you, Wes, for your question. Our next question comes from Cameron in Arizona.
Cameron, I'm a astronomy master's student from Arizona in the United States. I was just wondering if you guys had seen the latest Netflix special called Don't Look Up, which considers a comet coming to destroy Earth from the Oort Cloud. I was wondering what your thoughts were on the accuracy and what you guys thought of that movie. And to piggyback off that, about the Oort Cloud, we theorize with a high degree of confidence that it's there, but we haven't actually observed anything from it yet. So I was wondering if you knew of any programs that were currently in the works to try and detect actual Oort Cloud objects, like the one that was mentioned in that movie. So I love the show. Hope you have a great day.
Thank you, Cameron. We have talked about Don't Look Up before, and it's a movie that's received a lot of traction in the world of geeks. And it's a sort of a dark comedy. It's a bit tongue-in-cheek, but as Fred and I have discussed, very unlikely scenario given the monitoring that's going on. We'd be well aware of something like that long before they portrayed in the film. Would that be fair to say, Fred?
Yeah. I haven't seen the movie. You have,
yes,
but. That's correct. Look, I'm assuming that at the start of the movie, which is what we're being asked to comment on, they said there's an Oort Cloud object that's on its way in. If it's big enough to do damage, you're quite right, Andrew. We would have found it.
This one was purported to be 5 to 9 kilometers in diameter.
Yeah.
So that would do a bit of a.
It would be bright enough to. For all these telescopes, to detect it, and clearly that was the story in the movie because they knew it was coming.
Yes, but they knew too late.
They knew too late. Okay, right.
So yes, and it's a fun film. You shouldn't take it seriously. It certainly is leaning very far to the side of science fiction rather than reality. But they do have a lot of known processes in place that probably would be employed under the circumstances, notwithstanding the inept government decision makers. So that's fine. Now, the second half of Cameron's question is totally eluding me. The Oort Cloud.
Yeah, it's about whether we could detect Oort Cloud objects in situ, and could the James Webb Space Telescope see them? And it's a really interesting question. The Oort Cloud, of course, is it's a fifth of the way to Proxima Centauri. It's interstellar distance from the sun. It's this shell of objects which are what become comets when they fall into the inner solar system. They're icy bodies. Most of them seem to be relatively compact in size. That sort of 5 to 9 kilometers that you were just talking about there, that sort of size is what you would expect the typical
nothing to worry about
object to be. And Well, it's to worry about if one hits the Earth. But in terms of trying to see one of these things at the distance of the Oort Cloud, it's probably a non-starter. And there's a really interesting analysis of exactly this question, which is, I might just direct you to the nextbigfuture.com website and look up, if you Google direct imaging of Oort Cloud objects, it'll probably take you to this. And there's a really nice calculation done by an astronomer. I think his name is Brian Wang. He's certainly credited as the author of this page. But the calculation, which is very compelling, I've had a quick look through it, is that the typical Oort Cloud object is going to be at magnitude 41. Now, magnitude 7 is the faintest we can see with the unaided eye, and this is a logarithmic scale. So every 5 magnitudes is 100 times fainter. And so magnitude 41 is breathtakingly faint.
Right.
It is well beyond the limit of the James Webb, which is round about, it's about 21, I think. It might be, it's more like 30. The James Webb is about 30. And this is in a magnitude or brightness in the infrared wavelength region. Whereas the calculation is that it's about magnitude 41, 11 magnitudes fainter to see by the James Webb Space Telescope, which is a factor of about 100 billion. So what this really nice piece of work basically ends up with is the conclusion that if you want to detect dwarf planets in the Oort Cloud, and I can't remember what typical size. Yeah, they've talked about these are bigger Oort Cloud objects, 20 kilometers or so radius. So that would be big to start with for an Oort Cloud object. Yeah. If you want to detect one of those in the Oort Cloud, you need a space telescope with a mirror 11 kilometers in diameter, which we haven't got. We've got one 6.5 meters in diameter, or we will have by the time it's fully deployed, but not 11 kilometers. So no, the answer is we can't detect objects in the Oort Cloud, and there aren't any programs to try and do that.
That 11 kilometer one, I think, they're going to start working on that next week.
There was certainly, I've been involved actually with programs looking not for Oort Cloud objects, but distant Kuiper Belt objects way out there beyond the orbit of Neptune's trans-Neptunian objects, which are much nearer than the Oort Cloud, looking for them by the transit method. In other words, a bit like what TESS does, by looking for the dimming of a star as one of these things passes in front of it, because that would be on a timescale of probably milliseconds rather than minutes as the typical planetary transit is, or hours. But so far, I don't think there's been much progress with that kind of work. We were trying to do this with the UK Schmidt telescope when I was astronomer in charge at the Australian Astronomical Observatory, but we're using fibre optic systems to do it. And we didn't find anything.
Well, probably a good thing.
Yeah.
All right, Cameron, thanks so much for reaching out. Lovely to hear your voice too. And if you would like to ask us questions or send us questions, you can do that via our website, spacenutspodcast.com or spacenuts.io, and just click on the send us a question link or the AMA tab where you can do it the old-fashioned way and send us an email. I still can't believe we call that the old-fashioned way these days, but anyway, that's the way it is. One more thing before we go, Fred, there's a special event on this weekend, sort of celebrating your radio career with the Australian Broadcasting Corporation.
That's right. Yeah, it's hard to believe, but this coming Sunday is the 25th anniversary of my first regular slot with the ABC, the Australian Broadcasting Corporation. It was on a breakfast program in Sydney. It was a presenter who's still going strong. He does the late night program Nightlife here in Australia, or in New South Wales at the moment. His name's Philip Clark. And Philip thought it'd be a good idea to get an astronomer on. on his breakfast show. What he did actually, it was very clever. He sort of, they looked for people whose job was essentially overnight, and every day of the week they had a different person. This was a regular thing. My slot was, I think, Thursdays. So every Thursday, he thought he was getting an astronomer who was just going to bed because he'd been up all night. But of course, astronomers don't always work at night. We work a lot of the time during the day. But there were other people like people at the Sydney fruit market and people of that sort who work all night to get the fruit ready. The emergency doctor now, I'm sadly, I can't remember his name offhand, a very well-known head of emergency at, I think, Prince Alfred Hospital here in Sydney. He was also on this show, so people got their start in radio by having a job that the radio presenters thought would get them up early in the morning, or would have them going to bed early in the morning.
He could have just talked to the guy that was on before him every day.
He could have done that too. Anyway, it was great, and I talked to Philip for 2 years, and then sort of got handed over to other people over the 25 years. One of the other people I got handed over to was a fellow by the name of Andrew Dunkley.
Yeah, I remember getting a call saying, "Do you want to talk to this Fred fellow?" And do I have to? Now, I kind of inherited you from another person who worked at the same station as me, and she moved on, and I kind of picked up the baton, which I was very thrilled to do because I thought it was just a great thing to do in breakfast radio, and we did that for a decade.
It must have been about that, Andrew. Yes, I should check that. I probably have the
It
record.
might have been longer than that. I don't know. I was there 22 years, so I guess it could have been longer.
I think it was.
But, and we collaborated on a few things. We did a little bit of TV there for a while, and it's kind of manifested itself into Space Nuts.
Well, it metamorphosed into Space Nuts. That's right. So we are Space Nuts is the legacy of all that ABC stuff.
Yeah, it is. It is indeed. And of course, now we're on the community radio network across Australia. So we've been everywhere, man. Just by good fortune, we still are too. Yes, indeed. And it's great fun.
Yeah.
I hope you have a lovely afternoon tea with
we've got a little
folk on Sunday.
Drinks and nibblies with some ABC folk. Hopefully the weather will be clear. I don't know whether Philip is going to come because I haven't heard back from him, but certainly a number of other presenters. Robin Williams, who's one of the great names in science broadcasting here in Australia. He's been at it longer than I have, actually. He's been at it for 60 years. He said he might bring a tape recorder along to get some recollections and things like that.
That'd be lovely.
Yeah,
well, if you remember anybody that I might know, say hello for me.
I will.
I wish I could be there, but I doubt it.
Yeah, no, I'll make sure people know about Space Nuts.
They probably wouldn't let me in, Fred. So,
well, look, former station manager, they'd have to let you in, wouldn't they?
Oh, yeah, you never know. Yeah, there's no badge to prove it, though.
No.
All right. And congratulations on 25 years.
Still going strong, by the way.
Yeah. Oh, yeah, for sure.
On evenings now.
Oh, that's the best time slot for it, really.
It's nice. Yeah, 9:30. That suits me very well.
Indeed. All right. Thank you, Fred, as always. It's great to catch up, and thanks for spending some time with us again this week.
My pleasure, and Space Nuts rocks.
Yeah, it does. Moon rocks, particularly.
Moon rocks as well. Yes, that's right.
Magnetic connotations.
Yeah.
Thanks, Fred, and we'll see you next week. And from me, Andrew Dunkley, thank you so much again for joining us on Space Nuts. We'll catch you very soon on the very next episode. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Complete Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.